Gauss law and its applications. So let's go through introduction. I am Roshita from Sri Venkateshwar College of Engineering, Bangalore, studying in second year of EC department. So let's I am here to present you about Gauss law and its applications. So let's go through the introduction of Gauss law. Gauss law is a fundamental principle in electromagnetism. It relates the electric field in a closed surface to the charge enclosed within it. And this law is crucial for simplifying complex electric field calculations. So the mathematical formulation, Gauss law can be expressed mathematically as closed integral E into dA is equal to Q, where E is the electric field, A is surface area, and Q enclosed is the charge density of the surface. So epsilon is a vacuum permittivity, a constant that plays a vital role in electrostatistics. The concepts of electric field. So, electric flux is defined as a product of electric field and area vector. The total electric flux through a closed surface is directly related to the enclosed charge. Understanding electric flux is key to applying Gauss law effectively. So, symmetry. Gauss law is particularly useful in systems with high symmetry, where common symmetries include spherical, cylindrical, and planar geometries. Identifying symmetry simplifies the calculation of electric field significantly. So, applications spherical symmetry. For a charged sphere, the electric field outside behaves as if all charge were concentrated at the center. The electric field can be calculated using Gauss law with a spherical Gaussian surface. This principle aids in determining the behavior of electric fields in many physical situations. Applications. So first let's go to cylindrical symmetry. A long straight charged cylinder generates a uniform electric field outside its surface. By applying Gauss law with a cylindrical Gaussian surface, the electric field can be derived. This application is particularly relevant in understanding capacitors and transmission lines. Next, planar symmetry. An infinite charged plane creates a constant electric field on either side. So, using a flat Gaussian surface, Gauss law helps calculate the electric field strength. This application is fundamental in electrostatic problems involving charged plates. So let's see the relation to Coulomb's law. Gauss law is a generalization of Coulomb's law for all charge distributions. It provides an alternative method for calculating electric field without integrating. This relationship highlights the interconnectedness of different electrostatic principles. So Gauss law through non-uniform charge distributions. Gauss law can still apply to non-uniform charge distributions. The total enclosed charge can be calculated by integrating over the charged density. So this approach is invaluable in advanced electrostatic scenarios. So Gauss law in dielectrics. In materials with dielectric properties, Gauss law helps describe polarization effects. The electric field within a dielectric material. The electric field within a dielectric material can be derived from Gauss law. So understanding these effects is crucial for designing capacitors and other devices. Gauss law and capacitors. So Gauss law plays a significant role in analyzing parallel plate capacitors. The uniform electric field between the plates can be derived using Gauss law. This application is essential for understanding energy stored in capacitors. Gauss law in electric field lines. As shown in the figure, electric field lines visually represent the electric field around charges. Gauss law helps to determine the intensity of these field lines is a given area. So this visualization aids in understanding the behavior of electric fields. Next, limits of Gauss law. So Gauss law is not universally applicable. It requires closed surfaces and static fields. So it becomes less useful for irregular charge distributions without summary. So understanding its limitations is crucial for accurate problem solving. So let's see some applications of Gauss law in physics. So Gauss law is fundamentally in various physical fields including electrostatics and electrodynamics. It aids in solving complex problems involving electric fields and charge distributions. So many physical laws stems from this foundational principle of electromagnetism. Let's see these applications in engineering. Engineers can use Gauss law in designing electrical components and systems. It helps in analyzing fields around conductors and insulators. This application is crucial for ensuring safety and efficiency in electronic devices. Gauss law in astrophysics. So, in astrophysics, Gauss law can describe gravitational fields in a similar manner. It helps in understanding the distribution of mass in celestial bodies. So, this application aids in modeling gravitational interactions in the universe. So, in medical applications, Gauss law, medical images techniques or uses principles of Gauss law in certain modalities. So, understanding electric fields can improve imaging quality and diagnostics. So, these applications underscores the interdisciplinary relevance of Gauss law. So, historical context of Gauss law. Gauss law was formulated by mathematician Carl Friedrich Gauss in 19th century. It reflects the integration of mathematics and physics in understanding electromagnetism. So, this historical perspective enriches our understanding of scientific development. So, as shown in the image, these are some summary key points of Gauss law. So, coming to conclusion and future directions, Gauss law remains a fundamental concept in modern physics and engineering. So, future may explore its applications in emerging technologies like quantum computing. A strong grasp of Gauss law will remain relevant for future scientific advancements. So, feel free to modify or expand on any of these slides as needed. Thank you. Thank you.